Welcome to the Schreier Lab. We are an experimental research group where we study heterogeneous electrocatalysis. We aim to gain fundamental understanding of the electrochemical interface and complete kinetic studies in order to accomplish our main goal, close the anthropogenic carbon cycle utilizing electrochemistry. My name is Zach, and today I need your help to help me solve a mystery. The hydrocarbon economy is highly prevalent in our world today, where we use it to make fuels, plastics, manufactured goods, and high-value petrochemicals. Today, this is completely done using fossil fuel processes that utilize heat and contribute to harmful greenhouse gas emissions. However, here in the Schreier Lab, we aim to change this by using renewable energy sources to fuel this hydrocarbon cycle. To achieve this may sound like a big mystery, but I know the perfect place to start looking for clues: the lab. Let's head down there now. We're here at the Schreier Lab now. Let's go check out what all the other students are up to. Don't forget our safety equipment. Great, now that I have my PPE on, let's go search the lab for clues. Oh look, there's Meg. Let's see how her experiment's running and hopefully she can offer us some help. Hey Meg.
Hey Zach, my experiments are going well, but I saw this weird thing in the hood. Do you know what that is?
It's our first clue. Let's go check it out.
So what is this anyways?
So this is my actual experimental setup. This is one of our peak flow cells. It's one of the many types of cells that we use for our electrochemical experiments here. This allows us to implement things like electrolyte flow, gas diffusion electrodes, and allows us to analyze products through gas chromatography and NMR.
What reaction are you running?
So this is a type of reaction in here called electrochemical reduction of CO2.
That's so cool. What's that used for?
Yeah, the electrochemical reduction of carbon dioxide is really useful to combat the rising CO2 concentrations in our atmosphere, as it allows us to electrochemically transform the CO2 into fuels like methane and feedstock chemicals like ethylene. This simultaneously allows us to replace the current fossil fuel processes that you're used to make these same fuels and feedstock chemicals currently.
That's such a good idea.
Wait, I just realized why this is our first clue. The first step to close the anthropogenic carbon cycle is to electrochemically transform CO2 for the synthesis of fuels and feedstock chemicals. Hooray! We found our first clue! Wow, I'm so glad we were able to find our first clue. Let's go check the lab for more. I don't see it here by our purge box. I also don't see it on our other glove boxes or our gas distribution system. Wait, I think I see it down in the DEMS room. Let's go check it out. Yes, we found it, our second clue. Oh, hey Christine.
Hey Zach.
Are you running right now on the DEMS?
I am.
Can you tell me a little bit about what this instrument is?
Of course. So this is our differential electrochemical mass spectrometer, or DEMS. And what it does is it puts an electrochemical cell where we can run our reactions in close contact with a mass spectrometer. And this lets us get real-time information on what is happening on the surface and what products we're getting off as we change potentials.
Wow, that sounds great. Can you show me a little bit more about what that looks like?
Of course, let's take a look. So this is the program we use to run the DEMS. It gives us both the readings from the MS and information from our potentiostat so we can control the potential. So you can see as we do potential steps, we can measure both the current and the products that are coming off to get information about our system through each stage of the reaction.
Wow, Christine, that was really helpful. I really truly understand how the DEMS works now. But I still don't understand why the clue is here. We're trying to solve the mystery of closing the anthropogenic carbon cycle. How does the DEMS help us do that?
It's a great question, Zach. We use the DEMS for a lot of our valorization investigations, where we try to turn simple molecules like alkanes into something more complex that can be a platform chemical in industry. And the DEMS gives us insight into the basic reactivity to accomplish these challenging reactions.
Awesome, that makes perfect sense now. You cracked the code. Valorization is the second clue to solve our mystery. Thanks, Christine. Amazing, we just found our second clue. We're so close to solving this problem. And I think I might have an idea where the third clue will be. Great, now let's go check out what Jonathan's doing in the synthesis room. Oh, hey, Johnson.
Oh, hey, Zach.
What are you up to?
Oh, I'm just about to make some nanoparticles using wet chemistry.
Oh, awesome. How do you do that?
Well, the most important things of all to make nanoparticles, avoid them from oxidizing. With these shank lines, I can make these particles in inner gas. After the particle synthesis, I use this centrifuge to separate the particles from the solution and for further purification. For electrochemical studies, it is very important to keep the surface clean. And so we use these tube furnace to remove any source of surfactant that were used before we do an electrochemical study.
Awesome. And what do you do with your nanoparticles once they're synthesized?
That's a very good question. I use the particle to electrochemically oxidize the hydrocarbons into CO2 in order to extract energy out from them.
Oh, interesting. And this must be the cell you use. What instrument is being displayed here?
Oh, this is the rotating disc electrode. With this rotating disc electrode, you can study the kinetics of these processes, and so that we learn how to improve them.
Oh, interesting. And is this a part of the RDE, or is this our third and final clue?
Well, maybe you're not wrong. Because what we're trying to do here is to extract energy out using this electrochemical interface. So we are replacing the traditional fossil fuel combustion.
Oh, that makes complete sense. The third and final clue that we need is electrochemical combustion. Thanks for your help, Johnson. Way to go, everyone. We did it. We were able to solve the mystery of how to close the anthropogenic carbon cycle. Here in the Schreier Lab, we aim to first, electrochemically reduce carbon dioxide for the synthesis of fuels and feedstock chemicals. Secondly, transform these feedstock chemicals through electrochemical valorization into high-value added products. And thirdly, electrochemically extract energy from energy-dense chemicals, reproducing CO2 in the process that can be used in the synthesis step, thus closing the hydrocarbon economy. Ultimately, this electrochemistry can all be completed using renewable energy sources, and accomplishing our lab's aims will provide for a cleaner future. Now all we need is your help by considering joining the Schreier Lab and helping us pursue further research. Feel free to reach out to any of us grad students or to our advisor, Dr. Marcel Schreier, via email or Slack. Once again, I'm Zach, and thanks again for helping us solve the mystery today. Bye!
Oh, I'm just polishing a copper electrode. It might be useful in CO2 reduction.